So we'll discuss in detail the Krebs cycle. So this is a 3 NADH plus that will come in this step. In here one, here is one, and here is one. Total 3 NADH, and here in this conversion we'll get FADH2. This NADH and FADH2 will enter into the ETC cycle. Okay, so we'll discuss each and every step. First reaction, citrate synthesis. Citrate synthesis is an enzyme. Citrate formed from acetyl CoA and oxaloacetate. So by means of the condensation of the 4 carbon structure, and this is a 4 carbon structure and 2 carbon structure, these two will condense to give citrate, a 6 carbon structure. 6 carbon structure will form. So here citrate synthesis is an enzyme that will participate, and this is the only reaction where the CC bond formation will take place, will be seen. This 4 carbon and 2 carbon will combine and CC bond formation is seen here. Okay, next, so addition of the C2 units acetyl to the keto double bond of the C4 carbon. Keto group of this carbon is attaching oxaloacetate to produce 6 compound structure citrate. Next step, aconitase. So in this step, two reactions will be seen. In this, what is happening means the 6 carbon structure citrate is converting into isocitrate. That means isocitrate, the OH group. Here the OH group is shifting from this 3rd carbon to the 4th carbon, here OH. So iso, just shifting. So meanwhile, what is happening is this reaction is taking place in 2-step reaction. Citrate is converting into cis-aconate. Citrate is converting into cis-aconate intermediate, and after that cis-aconate will convert into isocitrate in presence of aconitase enzyme, where first removal of the water will be seen and it will form a cis-aconate structure, double bond, CC double bond will form. Then after that again the same water molecule will added to this and it will convert, that means shifting of the OH group will be seen. So citrate is converting into isocitrate by removal of water and addition of the water. Only stereoisomerism is taking place. In 3rd step, isocitrate dehydrogenase. Oxidative decarboxylation of isocitrate to alpha ketoglutarate. That means 6 carbon structure is converting into 6 carbon structure. 6 carbon structure is converting into 5 carbon structure by the removal of the water in the form of decarboxylation process. So oxidative decarboxylation of isocitrate to alpha ketoglutarate, a metabolic irreversible reaction. This is the irreversible reaction in this pathway where we cannot see the reversible reaction. So one of the 4 oxidation reduction reactions of the cycle. This is the first one where oxidation reduction is taking place. So first reaction, hydride ion from the C2 carbon. Hydride ion. What is the hydride ion means? This is the hydrogens that is carried by this NAD plus and it is converting into NADH. Here the first NADH is produced. First NADH plus, which will enter into the ETC cycle. Okay, so in the presence of isocitrate dehydrogenase. Next, by means of oxalosuccinate formation. So in first step, the isocitrate will convert into oxaloacetate, where the hydrogens will attach to the NAD plus and is converting into NADH reduced. NAD plus will reduce it to NADH plus H plus, and it is forming oxalosuccinate. And this oxalosuccinate, by removal of this carbon dioxide, it is converting into a 5-membered structure. It is converting into 5 carbon structure by means of removal of this carbon dioxide in the form of carbon dioxide. This is the 3rd reaction. Next reaction, conversion of alpha ketoglutarate to succinyl CoA. So conversion of alpha ketoglutarate is a ketoglutarate dehydrogenase is a complex enzyme. It is the same like pyruvate dehydrogenase. It is the same enzyme which we have seen, pyruvate dehydrogenase complex conversion of pyruvate to acetyl CoA. So here also E1, E2, E3 complexes are there. Alpha ketoglutarate dehydrogenase with TPP, then dihydroxylipoyl succinyl transferase with flexible lipomide prosthetic group, dihydroxylipoyl dehydrogenase is FAD. So this is the FAD which will carry the H plus ions, and this is a lipomide which will carry the SH group, that means coenzyme group, attachment of this coenzyme. So this will attach by means of this lipomide succinyl transferase, flexible transferase of acetyl coenzyme A to this alpha ketoglutarate, and it will convert into succinyl CoA. And dehydrogenase means it will remove the hydrogens, where NAD plus will convert into NADH. Okay, so this is the complex enzymes. So by removal of one carbon dioxide molecule, removal of one carbon molecule in the form of carbon dioxide, so it is converting 5-member ring, 5 carbon structure will convert into 4 carbon structure. So alpha ketoglutarate is converting into succinyl CoA by the formation of one NADH. So here second NADH is forming. Next, succinyl CoA synthetase. So in this, succinyl CoA will convert into succinate. Here free energy of thiazide bond of succinyl CoA is conserved as GTP. That means whatever the succinyl CoA transfer is there. Already we have discussed that coenzymes thiazide of CoA is a energy rich compound. Energy rich compounds in the table we have already discussed that. So this will have some energy. That energy will be formed in the form of GTP. So free energy of thiazide bond, this whatever the energy that is composed in this bond, that will be generated in the form of GTP, and GTP will convert into ATP. So this is the one of the substrate level phosphorylation. That means whenever a reaction is taking place between the two substrates, if ATP is generating, then that NTP is called as a that type of generation of ATP is called as a substrate level phosphorylation. Already we have discussed. So succinyl CoA will convert into succinate by the generation of GTP. This GTP will combine with the ADP, and it will give ATP and GDP. Again this GDP will be utilized for the reaction. So where this is called as a substrate level phosphorylation. Okay, next, so the succinate dehydrogenase complex, the complex of several properties and polypeptides with FAD group. So this is a group which is consisting of prosthetic group. That means this enzyme is consisting of FAD plus. So where these two hydrogens will be taken by this FAD, and it will reduce to FADH2, succinate dehydrogenase. That means this succinate is undergoing dehydrogenase process, removal of hydrogen, oxidation of succinate is taking place. So embedded in the intermitochondrial membrane. So what is happening means this FAD and FADH2 again it will enter into the ETC cycle to give ATP molecules by means of oxidative phosphorylation. So conversion of succinate to fumarate by means of succinate dehydrogenase enzyme. So it will give a transform of fumarate. Transform of fumarate will be formed, stereospecific structure. Next, fumarase. In this reaction, the stereospecific trans addition of water to the double bond. So by means of addition of the water, fumarase, in the presence of enzyme fumarate is converting into malate. So this is L-malate, L-isomer. L. So here left side position, that's why it is called as a L-isomer. L-malate will form in presence of fumarase. Fumarate will convert into malate in presence of fumarase by the addition of the water. It will form L-malate. Next, malate dehydrogenase. So in presence of malate dehydrogenase, again this malate will regenerate oxaloacetate. So here also these hydride groups, these two hydride groups will attach to this NAD and it will convert into NADH plus H plus. Again this is the third NAD plus NADH, third NADH. This will enter into the ETC cycle. Okay, this is the final step regeneration of the oxaloacetate, thereby third NADH plus H plus will be formed. So this is an overview of cycle, what is happening and what is going on. So here threes are the 3 NADH plus 1, 2, third, and here this is a GTP, will get ATP here, substrate phosphorylation, and here 1 FADH will be produced. So this is the Krebs cycle reactions. Okay.